Hello, my friends, and welcome to Arrays and Algorithms, lesson 204. So today, basically, we're going to go through some of the classic algorithms that you might use with an array and try and get rid of any of the problems that might pop up along the way. A lot of the algorithms that involve arrays, and we're going to see this a lot more later in the course when we focus on sorts, are going to involve a swap. There's a lot of different versions of swap that you can do. Sometimes it's a standalone method. Sometimes it's just these 3 lines of code in the middle of other algorithms. But a swap is essentially just changing locations. The big thing you have to be careful about a swap is that you don't overwrite data. So the key to a swap is having a temporary variable, here I'm just calling it temp, that can store one of the values. If you store the value that's inside the array at position I, you can then take position I and provide it with position j. So j goes into the I spot, and then you can put the temp into the j spot. This works whether it's an array of strings, an array of doubles, an array of objects, any kind of thing can be done with this swap. The only catch is temp has to be whatever is stored inside the array. So if the array is of ints, temp has to be of type int. Other than that, it's pretty straightforward. Max value. So max value, you're looking through an array and you're looking for the biggest thing you can find in the array. The big mistake that often is made here is that you mix up position with value. An array has 2 attributes for each slot. It has the slot number that you're in, and it also has the value of the contents in that slot. If you're finding yourself getting mixed up with this, you might want to think about an array of something else, like an array of strings. If you think about an array of strings, then it's a little bit clearer as to the difference between the number and the word that is stored. So here we're looking for the max value. So I want the value of the biggest number stored in my array. I'm going to have a variable called max, and I'm going to store the first value of the array in it. Now, it's a really good idea to use actual data from the array instead of making some sort of an assumption. If you make an assumption, because maybe you're going to start off at max is 0, just because you're thinking that's easily going to be overwritten, and you're going to find a number bigger than 0 along the way. Your array might be for NOAA, and maybe you're recording Arctic measurements for some experiment. If you're recording Arctic temperatures, then 0 is not actually a very good max, because you're not going to beat that if they're all negative numbers. So it's a good idea to actually get live data from your array instead of making some sort of an assumption. So I'm going to let max start off with the first value of the array. I'm going to loop starting at 0 just for convenience. I guess it would be more accurate to start at 1, but I'm just going to start from 0 for fun. Plus in the array, I++, if the current value of the array at position I, which I'm cycling through, is larger than max, it's the new winner. It's bigger than the old max. So the max will now be this value of the array. I'll continue looping all the way through, and one of 2 things will happen. Either I'll find a value bigger than my first guess, and I'll now store that in max, or my first guess was the biggest, and either way I will return it. Notice the fact that I don't want to return inside the if statement, because otherwise once I find one winner that's bigger than the first spot, it would be over. So I want to save the return until the for loop's totally done. Also note, just to try and, this is more of an editing choice for my part, to try and fit it in a PowerPoint slide, but I did not use any braces. The total if statement is thought of as one statement, and one statement inside of a for loop, I don't need braces. Minimum position. Now, the minimum value is actually starkly similar to the last slide. All you would do is change the inequality. But this is a slightly different algorithm. This is the minimum position. So I don't want to know what the lowest value is. I want to know where the lowest value is. So I'm going to set my min to 0, and I'm asking is this trouble? It's not trouble, because I'm claiming the minimum position is at 0, not the minimum value. So that's a safe assertion. I'm starting at 1 just because I can, just like I could start at 0, it really doesn't make a difference. And I'm going to ask myself, is the value of the array at min, currently 0, less than the value of the array at I? If that's true, greater than the value at I. If that's true, then I should be the lowest number, because this value is lower than that number, so this should be where the lowest number is at. So now I'm going to set my minimum to I. Once all said and done, I'm going to return min. So notice that slight difference between the lowest value and the position of the lowest value. Alright, so here we have some code. We have an array of integers with an initializer list. We've got our int min set to 4, and we've got a loop. This code doesn't really do much, because all it's checking is if min equals 4, min will now equal 3. Min initialized to 4, so min's automatically going to be 3, so it's not very efficient. I think a better example is down here on the bottom when we see the printout of the array list. We've got some /n's. and then a semicolon. This is an accumulator of a string, so our string can be used to accumulate all the facts, and then we just do one printout in the end. The actual array algorithm here is very weak. Oops, that's not what I wanted. You can see the live code, but that's not all that much better. Alright, so now we've got this array of doubles up top. I've got a total of 0.0. I'm looping through the array, and I'm accumulating each value of the array into total. I'm saying the array is that, and the total is that. That's a much better algorithm than the last one. We're being challenged to try and find the total and the average. Alright, I'm going to fork this. And let's see if we can find ourselves an average. So to find an average, you essentially want to find the total and then divide by the count. I've got two ways to find a count. I either could make a temporary variable right here, and I could say int count, and then inside the for loop, I could simply say count plus plus. And then to find our average, I could just say double average. You're going to find, as a coder, there's different opinions as to when you should make variables. It's a good habit to define all your variables up top, but as you look at some sources like maybe Stack Overflow, opinions are going to vary a little bit as to whether or not it's okay just to make a variable on the fly. If it's not a variable that you're planning on using for an extended period of time, it's more or less a throwaway variable, it's not all that horrible just to define it on the spot. So my average is going to be my total divided by my count. It's a very smart time to pause and make sure that I am doing double arithmetic, not int arithmetic. Luckily, total was defined as 0.0 in the beginning, and that pretty much makes me safe, because I know that total is going to be a double value, a floating point, divided by an int value, so it's going to be a double answer. And then I could just say average down here. An easier way to do this, a kind of built-in way, is instead of using count, I could just use array.length. Because my array is full, I don't have to worry about any gaps in the array, an array of 10,000 size but only 6 filled slots. So the array length is a very nice way to be able to save me the trouble of having to make this int variable and having to increment it through that for loop. Both work, just showing you options. Alright, so let's talk about inserting. Now in the last example I just pointed out the fact that it was a full array so we could take advantage of length. Sometimes you deal with arrays that are only partially filled. If an array is partially filled, it's usually a good habit to try and keep all the good data in the front of the array. So imagine the fact that I've got these 5 slots occupied, but then I have 10 slots after the fact. So I actually am managing how many slots are filled in my array. For whatever reason, I need to keep my data sorted, so I want to keep it in order. If I want to keep it in order, then trying to insert a 5, it has to be in between the 4 and the 6. Now, if these were physical objects like cards, I could easily just kind of nudge a 5 in there and make it work. But an array, I can't just nudge a spot in there, so what I actually have to do is make some room. I can push the 9 back, push the 8 back, push the 7 back, push the 6 back, and then I create room for the 5. Once I create room for that 5, I can just put a 5 in that spot. But I have to shuffle everybody else back first. 5. So the insertion code is going to be the exact same logic. I'm going to start at the last occupied index. It's not the end of my array, but it's the last occupied index, so I'd have to manage that actively on my own to be able to keep track of this. I'm going to let I do a countdown to the insertion point, where I'm actually trying to add the new thing. I minus minus because I'm counting down. Then I can take array at spot I plus 1 and have it equal to array spot I. So the spot on the right actually picks up the value from the spot on the left. Once I shuffle all the data, I now have 2 copies of the middle list data, I guess, and then I can set the array at that insertion point to the new value. Once I make that addition, I need to update my index last plus 1 to account for the fact that I've added a piece of data. So if we're going to talk about inserting, it's pretty natural that we then follow up with deleting. Now again, as we're still following this mindset of I have empty spots in my array after this 9, and I want to keep all of my data compact in the front of the array. So destroying the 6 is very easy. I can just make it go away, set it to 0 or set it to null, whatever I need to do to make it disappear. But now I have this gap in my data. If I have a gap in my data, I need to take all the data after it and move it forward to occupy that gap, so that all my good data is in the front of the array. It's kind of similar to defragging a hard drive. When you use the programs repeatedly, you end up with little pockets of information in your computer that are just wasted space. So defragging takes all the data in the computer and pushes it up to the front of the hard drive. So that 7 will advance, the 8 will advance, and the 9 will advance. And now I've essentially deleted that 6. So we can follow that same logic. For an insert, we start at the end and work towards the point of insertion. For a delete, we start at the deletion point and work our way out. And here, instead of saying I plus 1 equals I, we're going to say I equals I plus 1. The value at I will pick up the value after it, and that value will move forward. And then we'll just cycle through. Once all said and done, I'm just going to set index last minus minus to show my count is now less 1. Technically, if we were looking at that last slide, there's still 2 9s in my code, but because I've moved my index last, that second 9 I'm not looking at anymore. Some algorithms, if they're very worried about memory storage, they will destroy that 9 just to have it not hang out. But for our purposes here, it's quite all right just to have that 9 floating there as long as we don't look at it. All right, enjoy your lab.